of this extraordinary conference for inviting me, and to introduce what I'm going to talk about today, which a talk I've entitled Not Your Father's Complexity. And actually this is not a great title for non-native speakers, non-native English speakers, because it depends on you knowing a native English idiom, which is you talk about your father's something, like it's like, this is the way we always used to do it. So we knew about, so your father's complexity is the way we used to know about computational complexity, which is the way we used to know about how much it cost to execute programs, which is quite an important thing, it seems, for programmers to know about. So, here's a brief introduction to me. And if you've heard of, if you know, if you're in the Java world, you might have heard of me, possibly not, because I've written a couple of books. And the great thing about writing books is that they give you an opportunity to talk about what's in them, not once but twice. Because the first time you go around and you say, hey, I've written this brilliant book and it's really good and everyone should read it, and I'll tell you some interesting stuff that's in it. And then the second time you can go around again and say, well, actually, I got quite a few things wrong in this book and now I want to tell you what I got wrong. So, this talk is of the second variety. The book that I co-authored in way back in at the time of Java 5 was about Java generics. I'm always happy to say this is the best book devoted to Java generics, right? So if you want to know about Java generics, this is the book to buy. I know it's the best one. It's easy to tell because it's the only one. But I also wrote about collections in this. I mean, I actually wrote the collections half of this book, and I found out some interesting things. I had to think quite a lot about complexity, the cost of different collection algorithms in this. Collections are something that we use every day, so as Java programmers, and so the performance of collections is really important. So I thought about that quite a lot, and now looking back I think, well, actually, it's not so much that I got things exactly wrong, but I didn't know enough then, and certainly things have changed quite a lot since then, so that when you look at how expensive it is to use collections in Java, or actually in any other language or any other framework. It's not just, I will talk about the Java collections framework today, but the main message I want to get across to you is much wider than, applies much more widely than that. It applies, in fact, to any program executing on any modern hardware. Okay, so that's my introduction to what's going on here, and this is more introductory stuff which I don't want to talk about. So let's start off by thinking what your father's complexity was. So, I mean, a reasonable question. All right, I've mentioned already. It's a mental model of program performance which depends on you, which assumes that the number of instructions that are executed by a program is some kind of proxy for how expensive that program's going to be. For how long it's going to take, and that's the basis of sometimes really sophisticated calculations, which compute for a given data and for a given algorithm how many instructions are going to be executed. And the idea of a proxy is obviously it's a stand-in for the expense. and this is how normally we think about how expensive programs are going to be. That's been a model that's actually stood us in good stead for a long time, but I'm going to tell you now that we need to change this. It's not that the number of instructions executed is not relevant any longer. It is, but we want to see what else we need to know. So, if I'm going to talk about your father's complexity, I maybe should ask, who is your father? Well, I mean, I don't mean biologically, obviously, but who's your father in computing terms? So, here's a candidate for that job in the computing world. This is the guy who is most associated with the idea of computational complexity. Don Knuth, a giant in our field, the creator of tech, Turing Award laureate, and the author of The Art of Computer Programming, which is this amazing series of books, now not nearly so well known as it used to be and as it should be, in which he developed the ideas of computational complexity to a very high degree. So before I go on to talk about it, and this is all to do with performance, I should tell you that it's going to sound like I'm blaming Don Knuth for a focus on performance, which everybody suffers from. We all worry a lot about how fast our programs are. And what Knuth had to say about this, just as a kind of side note, was something that should really be very famous. Although he spent so much time talking about the expense of executing computer programs, what he said, the really important thing that he said was, we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. So that last sentence is still pretty well known. So people think far too much about performance, and almost all the time when you're worrying about performance, especially when you're worrying about performance before you've measured it, you're doing the wrong thing, because what you should be worrying about is how readable your code is, how well structured it is, how scalable it is, whether it's going to be modifiable, whether it's testable, all those things that are a badge of good practice. And you should only really be worrying about performance in the last minute, as it were, only when you know that there is a problem with performance, and only when you've measured where that problem is. So programmers often think, oh, I don't like the look of this code, it's going to be really expensive. But your intuition about where the expense of a program's execution lies is very unreliable. Hardly anybody knows what their program is really doing until they actually profile it and measure it. So that's kind of a side issue. I always talk a lot about performance, but I always want to drop in this thing which says, even though I'm talking about it, I shouldn't be doing, and you shouldn't be interested in it either. But we are all interested in it, so let's talk about it. So what is computational complexity? As Knuth didn't invent this idea, but he popularized it, and he used it a lot. So the Wikipedia definition says an algorithm with a time complexity of order of some function will complete in less than a number of steps which is a multiple of that function for some multiple and for a sufficiently large data set. So the idea is something like this. If you've got a graph here, the red line here is the actual cost of executing the algorithm. But the CG of n here, which is the function that we're interested in, provides an upper bound. Once you get past this should be n, I think. But if you get past the threshold here for a sufficiently large amount, you know that the complexity that you're using will always provide an upper bound to how expensive the program's going to be. So it's a kind of worst case thing. F of n will never go above CG of n there. So here's an example of the kind of formula that Knuth produces in many, many pages, and this is one of the simpler ones for a multiple list insertion sort. And he says the cost of doing a multiple list insertion sort is going to be 3.5 n squared plus 24.5 n plus 4n plus n, where n is the length of the lists that are being sorted, and m is the number of these lists that there are. So the detail of this doesn't matter, but the thing that's really interesting and important about this is to say that as far as for a sufficiently large n, all we really care about here is this term, the n squared term, because that's going to come to dominate everything. I mean, it doesn't matter how big the other factors are. In the limit, the n squared term is going to be the one that we really care about. And in fact, although people like to think a lot about complexity, and there are infinitely many different complexity functions, literally infinitely many. In fact, for practical algorithms, we're really only concerned with 4 of them. So so order 1 is when an operation takes constant time. Order, for example, looking at a lookup in a hash table. So insertion or lookup in a hash table under good conditions takes constant time. And if you double the size of the data, then it'll still take constant time. It'll still take the same time. Order log n means that if you double the amount of data, then you'll increase the execution time by a constant, and that would be, for example, binary search. That will have that effect. If you double the length of an array that you're doing a binary search on, then you're going to require to do one more. You're going to require to do one more search. So that'll be increased by a constant. Order n is doubled. Doubling the data doubles the execution time. So that'd be like linear search, where you're going to obviously have to go twice as far to find the thing you're interested in. And order n log n is typically for sorting. So that's a mixture of n and log n, and it's a bit worse than either of them. And these are actually the only ones that we care about, because above that, order n squared, for example, becomes infeasible for large data sets. So really, it's kind of quite limited. So I classified the various operations on the collections, on the Java collections library, and the different collections in the Java collections library for the book. And I had an interesting experience in doing that, because I was lucky enough to have, as a technical reviewer for the collections section of that book, this man. Another candidate for your father. This is a man who's very important to us, because this is Josh Bloch, author of Effective Java, which, by the way, is just about to appear in a 3rd edition. So this is like the Bible, or a Bible for Java programmers. Very important book. And Josh has not been active in Java for a really long time, but it appears that behind the scenes he's been rewriting Effective Java, and many of the ideas in Effective Java need to be updated. So this is very timely, this 3rd edition. So he's also the author of the Java Collections Framework. And one of the things that Josh told me in his review of the collections section of the book was that diagrams like this one that I had in the book were just completely the wrong thing to have. Right? So you see this in many books about Java collections, and in many blog posts and so forth. And the idea of this is that we've got a series of interfaces that are outlined in blue here, collection, list, set, and so forth. And we've got a whole bunch of abstract classes which implement those. And so I put a lot of that stuff in, and he said, take all that out again, because client programmers don't care about the abstract classes. And it's not particularly obvious when you first look at the Java Collections Framework. There's a whole lot of stuff there, and it's not clear what the design motivation behind it is. And what he told me was that the design motivation behind it is, this is an interface-based API, and a client programmer should choose the interface that they want according to the functionality they want. You know that you either want a set or a list or a queue, because you know what you want your program to do. You don't care about the abstract classes, which are an aid to implementers, to library writers. What you care about is, what is the collection going to do? And then, on the basis of having decided which interface you want, you then choose the implementation which fits your. You then choose the implementation which is the best one for your scenario, for the execution scenario that you're going to, usage scenario that you're going to have. So, for example, if you're going to have if you've got a list, and you know that what you're going to want to do is to add and remove elements from the beginning of the list a lot, then maybe you want to think, is array list the right thing for me to use? Because when you add an element or remove an element from the beginning of an array list, you're going to have to shuffle all the elements of the array list up or down in the array, because array lists are 0 indexed. Right? So adding or removing an element from the beginning of an array list is order n, is linear in the amount of data in the array list. Whereas a linked list, which implements the same interface, is one in which you can simply add or remove a cell from the linked list, and that will allow you to perform that operation in constant time. It's just a matter of allocating some memory if you're adding an element, and swinging a pointer or two, and the same for removing it without even allocating the memory. So that in principle seems like a choice, a way of choosing between list implementations. So you get tables like this one, which I had in the book, and this one is taken from the book, where we say, well, for an array list, getting an element from a random position is linear. Is constant time, because with an array, you can just index into it wherever you want. That takes no time. Whereas for a linked list, you're going to have to step along the list until you find, say, the 323rd element. You're going to have to do 323 steps to get to it. So if you've got lots of random access elements, random access into the list, then you want an array list, not a linked list. But if you're adding, say if you're going to be removing a lot of elements from the beginning of the list, then doing that on an array list is order n, whereas doing it on a linked list is constant time, because you're just removing a cell. So did this ever make sense? Well, the answer is yes, it did, and it still does. But you need to believe in some assumptions. I mean, if these assumptions hold, then this is okay. So the first assumption is you can ignore constant factors. And that may or may not be true. So, for example, this is quite deceptive, because the operation that's going to be executed here is system.arrayCopy, which is linear. It is linear in terms of the amount of data there is, but the operation is intensified. So it's directly translated to native code, and it's a very fast operation on modern hardware. So although, in principle, it's order n, it may be that the proportionality factor may actually really influence your decision. So perhaps an array would have to be absolutely enormous before system.arrayCopy would really become very expensive, just because that particular operation is cheap. So something else to think about is, do all instructions actually have the same duration? Because classically, algorithm complexity just counts the number of instructions. So I put an extra bit of information into this slide this morning, because I discovered, or I went to a talk which explained that the way Ethereum works is that the Ethereum virtual machine has a cost attached to each operation. So I actually found what these costs are. So Ethereum, the blockchain algorithm, has this idea: if you want to submit some work to an Ethereum network, then what you have to do is you have to supply an amount of, quote, money, they call it gas, that correlates to the cost that is going to be for that operation. So you've actually got to invest in getting it performed, and that's because the same operation is going to be performed by every node on the network. So it's fantastically redundant, and so you've got to pay for it. And so there's actually a money cost attached to each of these things. And you can see that the Ethereum virtual machine, this is like bytecode instructions here, actually have a cost attached to each one of them. And how much a unit of gas costs depends on, it's a certain number of ethers, and obviously how much an ether costs depends on the day of the week. I mean, last week it was a lot less than this week, and next week it'll be, an ether will cost twice as much. But what's quite interesting here is that there's a recognition there that operations don't all cost the same. And the more of these very expensive things that you do, I mean, this is only part of the table. The table goes on a long way. And more of these really expensive things you do, the more you're going to have to pay for it, literally pay for it in terms of money. But what's still quite interesting about that is they're still thinking in terms of, this is the unit cost of a single instruction. Like an add always costs 2 gas. And we're going to see today that actually you don't know how much an addition operation is going to cost. It might be very cheap, and actually we're going to see it might be very expensive, and we'll see why. So it's not true that all instructions have the same operation, have the same duration. We know that, for example, divide is much more expensive than add. There's an assumption that memory doesn't matter, even though there is a notion of space complexity, which is parallel to time complexity. How much is the memory footprint of a program? Nobody seems to care very much about that. So we're going to see that memory matters a lot. And finally, the really important assumption is that instructional execution is the most expensive thing that your program has to do. So the assumption always was that basically all other costs are unimportant compared to the cost of actually doing the operations on your data. Is this true? Well, it was true, actually. But I mean, of course, it never was true that instruction execution was the only bottleneck. So there's plenty of others. And as we know, if we want to analyze the performance of a program in the system as a whole, we have to think about the costs of the hard disk transfers, of the network, of garbage collection for the JVM is a big deal, resource contention, and a lot of other costs as well. And there's a kind of classic thing which all people who've been involved with performance tuning know that if you get rid of one bottleneck, you think, oh, here's my data flowing through here, and if I can just get rid of that bottleneck, then everything will go really well. And of course, what happens is it reveals another bottleneck further down the line that you didn't see before, because it was hidden by the first one, and actually you make things worse because you're putting more pressure on that. So the idea, but setting that on one side, let's think about why they thought that why this classical model assumes that instruction and execution is the most important thing. So basically this depends on a model of computing that I learned when I started learning about computing, and I thought was never going to change, which is that you have some data that comes into the CPU, and the CPU is probably going to retrieve it. The mainstream is it's going to retrieve data from memory, and it's going to you've got an arithmetic logic unit which is going to do the work of operating on that data, and it's going to store it back in memory again. And you've got input and you've got output, but that's the kind of main line of what's going on. And prior to about 1980, that was a pretty straightforward model of how things worked. So what happened then? Well, I couldn't help, actually, thinking about pre-1980 computers, finding some pictures of pre-1980 computers. This is a picture of something called a machine hall, which nobody remembers now, but I just can't help it. This is the scene of my youth, and you'd have a room like 3 times the size of this one, with massive banks of computers, and the power in these things was about the same as you've got on your mobile phone, probably less than you've got on your mobile phone. And something really nice I just couldn't resist telling you about was the fact that in those days, for some reason, every computer in this class of things called a mini computer, which wasn't like the things in the machine hall but smaller, they always would put them in a garden in order to take the advertising pictures of them. I have no idea why, but they always did. And there was always an extra accessory that they added as well. You were never without one of these decorations to your advert for a mini computer. But actually, what was the problem for me in finding there was a suitable slide to show you was to find one in which the woman in the picture was as decorously, as discreetly dressed as that. Usually, they had a lot fewer clothes on. So that was in the 1970s. In the 1970s, this is the golden age of complexity. I call this the golden age of complexity analysis. So what was going on was the really central thing was that at that time, prior to 1980, in the mid-70s, say, late 70s, the cost of memory was $1 per byte, right? About. That order. So just think about that for a moment. Think about the size of memories that we have now. And between 1980 and 2010, this is what happened to the cost of memory. It went down. And of course, this is a logarithmic scale. So it's gone down by a factor of about 100,000. So it makes Bitcoin look quite normal, really, doesn't it? And the interesting thing about this is what it meant for analysis of program execution. Here, memory was really expensive, so you couldn't actually afford, you could afford so little of it. I mean, think of it, at $1 per byte. And so for example, sorting algorithms, the things that everybody used for sorting were called external sorting algorithms. And external sorting algorithms were very ingenious ways of ensuring that you could actually manage to sort an entire data structure even when you couldn't get most of it into memory. So you could take a little bit into memory and you sort that, and you put it back onto the disk again, and you get another bit and you sort that, and then you somehow manage to combine the two together. So external sorting was this really big deal. And it's clear that in that situation, with a lot of switching backwards and swapping backwards and forwards to disk, the cost of those transfers would dominate your program performance. That was by far the most expensive thing. Then the cost of memory came down, and we got the golden age of complexity analysis, because now memory is cheap enough to get all of your data into memory, and it's and now it's the execution of the instructions that's the most that is now the dominant cost, because we only need to do one disk transfer, and then we can get to work on this big sorting problem that we've got. So what happened? Well, what happened was this. While the cost of memory went down like that, the performance of memory went up like this. So that was actually, that looks pretty good. Over 30 years, 30 years. Over 30 years or so, you've got a tenfold increase in the performance of memory. Most technologies would be very happy with that. If aeroplanes were going 10 times as fast as they were doing 30 years ago, you'd think that was pretty good. Or whatever, the usual comparisons with technology. Very few of them improve at so fast. But the really interesting thing is what happened to the performance of processors. And they didn't go up by a factor of 10, they went up by a factor of 10,000. And what that means is that suddenly the processors can go so much faster than memory can supply the data that you've got a big problem. And the problem is that if you're not careful, and hardware designers are extremely careful, so they try really hard to stop this from happening. These processors are going to be sitting there waiting for data because the memory can't get it to them fast enough. So keeping the cores running today involves a kind of stack of caches. This is how it works. So you've got memory is really kind of the slowest element of that, and then you've got a last level cache. Typically, processors nowadays have three levels of cache. I mean, what's in your laptop will have 3 levels of cache. They're becoming increasingly, as you go up here, they become smaller and smaller, and they become faster and faster. So to retrieve the data from memory really takes a long time, but to retrieve it from the top level cache, from level 1, is really fast because that's actually almost comparable with the speed of with the speed of the processors. And you can think of the data that's going through that's coming up from the memory as being a kind of pipeline. It's often talked about that. Talked about as a pipeline, and you can kind of generalize this to think about a memory hierarchy, which actually has everything on it, right down through solid state, right down through SD-RAM to solid state drives to mechanical hard disks, and basically it's the hierarchy has a really clear rule about it. The capacity goes up as you go down. The speed is obviously going to increase the nearer you get to the processor, and by the way, the power it's going to consume is going to get nearer. So this is the constraint that holds up hardware designers. They've got to think, how on earth are they going to be able to get enough, to be able to get the data near enough to the cores for it to be able to work with. So typically the difference, the cost of getting data from each level increases by a factor of about 3 or 4 as you go down the levels, something like that. So in my MacBook Pro here, it's a 3 gigahertz processor. So one cycle on this is a third of a nanosecond. Level 1 cache is about 1 nanosecond. Level 2 cache is about 4 nanoseconds. So we're going up by a factor of 3 or 4. Level 3 is 16 nanoseconds. Then main memory is a disaster. It's 100. It's 100 nanoseconds or so. So it just takes a really, really long time to fetch something up. So the way I like sometimes to explain this is to imagine that, because you think, wait a second, 100 nanoseconds, that's really fast, isn't it? But from the point of view of the processor, it's really, really slow. So I'm a person standing at the cooker, and I'm boiling eggs. I choose this because everybody knows how long it takes to boil an egg. It takes 3 minutes, right? So I'm getting a supply of eggs. This is the data that's coming to me. And each one I get, I put it in the pan, I boil it. That's an operation. Right? So the eggs have to come from memory, which is the fridge at the other side of the kitchen. So, and I've got this kind of chain of people that's the caches that are passing the eggs up to me. Right? As long as they keep on passing them to me, I'm all right, because I can take another egg and I can boil it. But supposing something goes wrong, supposing they all drop their eggs, that happens quite frequently because, like the pipeline, there's a pipeline stall because your program has jumped to an unexpected place, and all the data that you were expecting to use is no good, and they've got to start again and get the eggs out of a different part of the fridge. Well, to come from the fridge to the cooker takes about 300 times as long as it takes me to boil an egg. So I want to boil an egg, and it's going to take me only 3 minutes to boil it when it arrives, but I'm going to have to wait 900 minutes for it to come. 900 minutes, that's about 15 hours, 16 hours. So I'm drumming my fingers on the cooker, waiting for all that time. That's a huge waste of your processor power. And don't even get me started on what's going to happen if the eggs in the fridge aren't the right ones, because we've got to go out to disk. That's like going out to the shops. That's a factor of another 100 or more times, probably nearer 1,000 times. So now we're waiting. If I have to wait for that, I'll be waiting literally years, 2 or 3 years, for it to get my next egg. So of course, for disk transfers, we never do wait. But sometimes we have to wait for the memory. That's really a problem. Here's a picture I got that I think is kind of quite nice. I was looking for a long time for something like this. This is how they put fires out in Mongolia, or how they put them out in Mongolia in 1977. It's a stamp to show the way it's done. So you can think of this as the picture of how the caches work, except for it to be realistic, you'd have to have like 20 people standing on the river's edge, and then 10 people standing here, and then like 2 people standing there, but they'd be really fast, and then passing them up there. So this is really important. So the key thing the key takeaway from this talk is cache effects are really important. Main memory retrieval costs are going to be 300 times as slow as register access. Typical programs, because hardware architects are dead clever and work really hard on this, typical programs have a 95% hit rate in the cache. So you think, what can the problem be? Well, the problem is that other 5% is extremely expensive. And if you don't get it right, that will dominate. That 5% will actually dominate the cost of your program execution. So where does this 5% come from? Well, there are a lot of reasons. People write huge books about how hardware works and how caching works in particular. But there's 2 that I'm going to talk about here that you can see the impact of them on your program. And one of them is insufficient capacity in the caches. You can't do much about that. And the other one is a failure of prefetching. So you might be able to do something about that. What's prefetching? So here's a picture of. In this, I've just got the first level 1 cache here, so there's a lot more stuff. This is a highly simplified picture. Processor, level 1 cache, main memory. And so level 1 cache, which is typically in 64-byte units, that have to be refreshed or stored as a whole. You can't pick and choose between the data in them. These things correlate with different elements of memory. So the way that stride prefetching works is that the processor can observe what's going on with your access to memory. Supposing I'm going to access the memory in a very regular way, right? So there's even strides through the memory. Then the hardware can read that and say, oh right, I'm going to make a guess as to where the next part of memory. Next data, where the next data elements are that you're going to want to access. It's obviously just going to be that. And it can prefetch those and bring them up into the cache before they're actually needed. Now, obviously, it's not always going to be right, but if you think about executing, supposing you're processing an array, and you're going to do this like 100,000 or 1,000,000 times, you're going to step through the array lots and lots of times, then actually stride prefetching is going to be very effective because it'll be right nearly all the time. Of course, it won't be right at the point when the loop exits, but that's only once out of 100,000 or 1,000,000 iterations. So overall, stride prefetching is a real winner if you can do it. Of course, we're object-oriented programmers. Object-oriented programming relies really heavily on pointers. So actually, if you've got an array of objects, you don't know where those objects are in memory. So it's quite likely that, in fact, you're jumping about in memory and you're going to completely frustrate stride prefetching. Now, and this is kind of a central problem that is going to afflict all object-oriented programmers in a naive implementation of object orientation, which is what we've got at the moment. It's actually a little bit worse than that, because, in fact, what I haven't told you is that as well as the cost of getting data into memory, there's a cost of finding it in the first place, because memory is divided into pages, typically 4K, and these pages have to be found. The processor doesn't use an absolute addressing for memory. It uses virtual addressing. And the reason for that, the kind of strongest reason for that is kind of obvious, is that it wants to know that the data you're trying to access belongs to the process that it wants. So you're not going to go across process boundaries. So the virtual address ensures, if you're only looking at a virtual address, it ensures that the data you're trying to access belongs to the process that you're currently executing. Now, that's a really important safeguard, and it's actually the foundation of stability in modern operating systems. So nobody's going to give that away. And by and large, processors always use a virtual address. A page index, you check whether this page belongs to the process that is trying to access it. and an offset within the page. So, but how are you going to find out what physical address that belongs to? Well, you're going to need to have a lookup table. And what's the lookup table going to be? Well, it's a map from the page index to the actual physical address, and then you add the offset on. But how are you going to get at that? Because the page table is usually quite large, so it's going to be stored in memory. So how are you going to get it from memory? Well, you can see where this is going. So you've got a cache for the page table as well, which is called the translation buffer, or sometimes the translation look-aside buffer, if you come across that term. I don't know why. And that is relatively small. And any time that you try to hit a page that hasn't been cached there, you're going to have another transfer from memory, which is going to take another 15 hours to get up from memory into there. So jumping about the way I showed you between pages carries a double penalty. It's not only that you're going to frustrate stride prefetching, but you're also going to cause lots of translation buffer lookups. It's a bit of a disaster. So that's the outline of the situation. So the question is, what does this mean for us as programmers? That's the background. What does it mean for us as programmers? Well, let's have a look at I talked about two issues. I talked about cache capacity, and I talked about stride prefetching. And I'm just going to show some examples of how these things can work out. So I'm going to, in this first example, I'm going to compare traversing a linked list with traversing a primitive array. So you might say, well, like, everybody knows linked list is a problem. Why don't you compare linked list with array list to see what happens? Well, I'll tell you why in a minute. But at the moment, this is what we're going to do. So here are the results that I got using the Java benchmarking harness, micro benchmarking harness, JMH, and attaching the Unix tool perf to it. I don't have time to go through that now, but perf allows you to see the hardware counters, and the hardware counters can actually be configured to count how many cache misses there are. So we can take a look and see what happens when we try traversing a linked list with 1,000 elements, 7,000 elements, 63K, and 511K. And the first thing that we see is that the performance for this very straightforward test goes down dramatically as the list gets larger. So you say, why is this happening? Well, we can look a bit at what perf told us about what's happening within the hardware, and we can see pretty easily what's happening. So here's a measure that hardware engineers use all the time. It's called the clock ticks per instruction. So in general, modern hardware, because of instruction level parallelism, can perform more than one operation per cycle. This is pretty clever stuff. And a measure of how well an algorithm is performing is what the CPI is. Sometimes it's the other way around. It's instructions per clock tick, but it's the same idea. So here we're getting about 3 instructions being executed for each clock tick, which is pretty good. And here for the larger one, we're getting 1.33. So sorry, it's clock ticks per instruction there. So it's gone down from pretty good to pretty disastrous. That's really quite bad. And if we now look at the things in the number of things that are happening in terms of an operation, the operations now are going to be like stepping along the list. It is Java operation now, not a CPU operation. Then what we see is that the number of cycles for each operation on the list is going up pretty much in the same kind of way as the performance is going down. So clearly there's a big problem there. Interestingly, though, the number of instructions that are being performed for each operation is just exactly the same. In other words, this really is an order n. It genuinely is an order n algorithm. So, like, the number of instructions that are needed to be done computationally, if you just looked at what the machine code is doing for this for this linked list, you'd think, hey, this is just great because it's doing exactly the same thing, no matter how long the list is. Right? The fact that that's constant tells you that according to classic algorithm analysis, should tell you that the performance will be the same, but we see it clearly isn't. And if we look a bit further, we can find out why not. Is the level 1 data cache load misses, and you can see that that's going up from an average of 1.18 per operation to 2.65 per operation. Now that's really a lot of data misses. And if you think what I said earlier, which is that it's the misses that really hurt you. So a cache miss, sorry, is when you're looking for the data in the level 1 cache and you're not finding it because of, well, we're going to see why. But the key thing is, if you don't find it, then you've got to fetch it from memory. And when you're getting that number of misses, of cache misses per operation, that's going to dominate. That's totally going to dominate, and you can see that it is doing in this table. So we can go on and look at a few other things like this. I think the last level cache is that's the one that's nearest to the memory. Even that one's starting to look bad by the end there. And really, it's the cache misses that explain why this is going so badly wrong. And you might ask, well, like, what's that about? And I'll tell you that in a moment. But yeah. Oh, and even the translation buffer. So this last line here, the DLTB misses. That's when what's happening is that we've jumped over a page boundary, and we've had to reload the page table. So that's going to be doubly expensive. Okay, what's going on there is that a linked list node occupies 24 bytes. And in this, we were running on an Intel Core i5, not my machine, but one similar to that. And actually, although I put this table in, we really only care about this. The level 1 data cache is 32K. Each new list item is going to be 40 bytes. That's 24 overall. So that's 24 for the cell, the linked list cell, and another 16 for the integer object, because I'm using a linked list of integers here. So the level 1 cache is going to be full at less than 1K of items. And you can see that obviously what we had, I mean, that's unrealistically small for any practical data structure. So you're just going to need to be refreshing the cache the whole time. And the reason that I didn't compare with array list is because array list is not actually that different. It's true that the overhead for an array list is much less, because it only needs to have one extra reference for each new item in it, unlike the linked list, which needs to have instead of the 24 bytes that the linked list needs for each new item, it only needs 4. But the array list, but the real cost is the size of the integer objects. I just chose integer as an example here. But every integer object takes 16 bytes, because objects are just really expensive in Java. There's a pointer to the class, to the class object, and there's a whole lot of data. Every object's a monitor, and the bits have to be stored for that. Objects are big. They're minimum 16 bytes for an integer. And so overall, you've got 20 bytes instead of 40. So basically, you're going to blow the cache when you've got a 2K of items in there, and it's still really bad. Take a quick look at how it works for a primitive array, and you see that it's really different. So the performance for this is just absolutely level, and the reason the performance for that is level is because there are no cache misses, basically. I mean, there's almost no level 1 cache misses, and there are no last level cache misses or translation buffer misses at all. So, like, why is that? Well, the answer is really obvious, because arrays are their data is really well organized, and they're really compact. So here's something I've got to step back on. When we were writing the book on generics and collections, we wrote in that book that arrays, primitive arrays, well, arrays of any kind in Java, were a legacy data structure, on the grounds that, hey, you can do so much more with collections. And functionally, arrays are a disaster. You know, in terms of how they fit into the type system and so on. Arrays shouldn't be there in Java any longer. But in performance terms, we're a long way from being able to get rid of them, that's for sure. Okay, so that was the first example I wanted to look at, which was just simply a cache capacity problem. Here's a second example, a second issue, which is data locality. And this fits in with the stride prefetching thing I talked about. So there are two problems. One of them is data density. So how much of the 64 bytes, every time you put 64 bytes into into a cache line, how much of that is data you actually need, and how much of it is actually, so for example, supposing you've got a 4-byte piece of memory and you want to look at that, you're going to have to load in 64 bytes. And so most of your cache line, I mean, if that belongs to some other data structure, most of your cache line is going to be given over to the wrong thing. Stuff that you don't actually want at this moment. And basically, therefore, you're just going to have a lot more cache refreshes than you should really need. And for prefetching, well, we've looked at that. Are you giving the processor a decent chance of helping? So here's my experiment here. I populated a linked list in 2 different ways. First of all, I populated it, as I like to say, naturally. I mean, that's just my term for it. It's basically, this is the algorithm. So basically, I just kind of create, I just incrementally add elements to the linked list. And the hope is that it's going to be organized contiguously, like this, so everything's going to be together. Traversing over this should allow a decent chance of getting allowing the processor to predict where it's going to go. And the alternative is I'm populating it randomly. And what I do is I create an array list and set up all the and just allocate integers in what I think is probably going to be contiguously there. But then I choose to create a linked list in which what I'm going to do is I'm going to populate each element of the linked list from something that's chosen randomly from within here. So the elements of the linked list now are going to be randomly chosen from that array on the right. So I used to show a demo of running this a performance test in a talk, but it just takes too long. So I did the next best thing, because everyone likes a demo. So what I've done instead is, this is a JMH that's running on using perf, and the idea of this is, I speeded it up a lot so that it would fit into the talk. And the idea is this: we're going to compare what it's like traversing down those 2 linked lists, the one that was populated naturally and the one that was populated randomly. They're exactly the same data, they're exactly the same size, there's nothing different about them at all except the way they're organized in memory. And the results are kind of, I think are pretty convincing. It takes slightly too long for this demo to run. I think in practice it takes something like about 5 minutes, which is way too long for a talk. So I've speeded it up a lot. Performance tests just have to be, you have to be kind of patient with them. So we'll get there in a moment. And there you are. That's the difference between the 2 different between those 2 different executions. The data is exactly the same, the number of instructions executed exactly the same. All that's different is just how they're organized in memory. So there's a real lesson here for us, isn't there? Actually, there's 2 lessons. One of them is we want to watch what we're doing really carefully about how data is organized in memory, and the other one is not to use linked list. Poor unloved linked list. I really feel for it. Linked list was written by Josh, and this is what he tweeted a little while back. Nobody loves linked list. So, okay, so I'm coming to the end now. I've talked about most of what I'm going to do. I'll have to skip over these slides about HashMap. HashMap, again, the point of these slides about HashMap is that what you think about as being the problem with a HashMap, the kind of worrying thing about performance for a HashMap, is going to be when you get overflow. So when you get collisions on the buckets of a hash map, and you get overflow, not like this but like this, and then you get a linked data structure. So you think, well, that's going to be expensive, and in the end it's going to turn linear, or in the case of Java 8 and onwards, it's going to be like you have instead a binary tree here. But what I'm telling you now is, although you're going to have to pay for the steps along a linked chain, it's actually much worse than that, because those steps are liable to involve cache refreshes, and they're going to be dead expensive. So there's some progress in terms of the immutable collections in Java 9, which allow you to at least keep the key and value pointers. They allow you to construct an immutable array of the pointers, key value pointers, and that means that at least these will be contiguous. And there's a kind of possibility, I think, that I haven't experimented with this, but I want to do this. That one thing you might do to improve performance, if you've got a large map, would be if you happen to be in the situation where that map is created, and then it's going to be read much more than it's going to be written subsequently, is what you might do is actually import it into an immutable collection, and then that way you'd get all of the you'd get the contiguity of the pointers, and you'd also get pretty good data locality for the data as well. But you'd have to bring it in after it had been created. You can't do that dynamically. So reducing memory footprint is an objective of many of the collections frameworks. Everybody knows about this problem in Java, but nobody really knows, well, there's only kind of tentative steps to doing anything about it. So I'm not going to go through all of these third-party collection frameworks. Some of them are very good, and they're very fast, and they like to talk about reducing memory footprints, but they don't usually spend any time thinking particularly about cache friendliness. If you want to think about cache friendliness in particular, then there are some libraries that do this. So Object Layout is a library invented by Gil Tenney and Martin Thompson, who are kind of foremost in this field in terms of thinking about this particular problem. Martin Thompson writes a blog called Mechanical Sympathy, which I'd very strongly recommend because he's the guy who turned me on to this problem in the first place. So the idea of object layout is that essentially it allows you, it's like a C-style array of structs. That's the notion. So you can see it creates an array. Of course, it's got to be immutable. You lose all the operations on this thing, but it will allow very fast processing, and it'll also allow you to put an array on the end of it as well. So it's a bit more like writing in C. Every time I give this talk, somebody comes up to me afterwards and says, "Have you heard about this collections framework?" And I say, "Oh no, actually, I haven't." So roaring bitmaps is one that I got told about in that kind of way, and I haven't had a chance to investigate it. But since it's based on bitmaps, you would expect that the compaction of data there will mean that it should be very fast. And the big temptation in the end is Project Valhalla. So that's still a bit of a way down the line, but that will come into Java, and that will mitigate these problems a lot. It'll improve things a lot. The idea of Project Valhalla is to create value objects. So value objects are things which the language will know. If you use one of these things, it'll know that you kind of mean to have an object, but it will implement them as a primitive, effectively. So that's really that's pretty difficult to do, and a lot of thought is going into that right now. And so you'll be able to have, for example, collections of primitives, which is obviously what we really want. In order to get primitives now, we have to have arrays, and arrays are a legacy data structure. So collections of primitives really will be the kind of big value out of Valhalla. Okay, so I'm past the end of my time. Conclusion of sorts is that performance doesn't matter. 97% of the time, it doesn't matter. But the 3% of the time it matters, it really does matter. You never get a performance improvement without some kind of trade-off. So the kind of for example, you could give up immutability. You could give up mutability and go for immutable data structures. You'll get a lot of improvement in performance. You'll lose a lot of functionality. There are many other examples like that. Algorithm complexity is still important, despite the theme of the talk, but so are a lot of other things: network and database performance, garbage collection, resource contention, and above all, caching. So even though, despite the title of the talk, I said it's not your father's complexity, but actually it really still is your father's complexity. It's just got a lot more complicated. Thank you for your attention.